Okay, today I want to skip to the end of the presentation, and there is one slide at the end regarding Bode plots that I want to cover. And the reason I want to do so is because there is a short answer question on the homework that's due tomorrow. So we will cover Bode plots in detail on Wednesday, but I do want to talk about this slide. So let's see. Page 25. Okay. H.W. Bode was an engineer who was working at Bell Labs in about early to mid 1930s. And he came up with this graphical description of the frequency response of electrical circuits. The way we use it for filters is we use it to display the frequency characteristics of our low pass and high pass filter circuits. What it is basically it's a graphical approximation. We use straight line approximations known as asymptotes to draw out our frequency response. So the image here is for a low pass filter. Let's explain how to look for a Bode plot. So we have our break frequency, right? We have our break frequency, FB. Frequencies to the left of FB are the low frequencies. Frequencies to the high are the high frequencies. Frequencies to the right, right? FB is our border. It's the transition point between the pass band and the block band. If it's a low pass filter, these frequencies on the left are passed. Frequencies on the right are blocked. But no matter what kind of filter it is, once you have your break frequency or cutoff frequency, frequencies to the left of FB are always low frequency, considered as low frequencies. Frequencies to the to the right side are always considered to be high frequencies. Doesn't matter what kind of filter it is. So what Bode plots do is you take asymptotes. Asymptotes are straight line approximations to curves, right? In geometry, in standard geometry, asymptotes are defined as straight line approximations. Okay, these straight line approximations allow us to describe the frequency response just by drawing two straight lines. Similar to kind of piecewise linear analysis. You can break it up into individual pieces, and each piece is linear. Okay, so for a low pass filter, on the figure in the left, you can see low frequency asymptote is right here. The high frequency asymptote is labeled here. This portion is the low frequency asymptote. In this portion right here is the high frequency asymptote. So straight line and then straight line in both places. It's a little bit hard to visualize on the left, so I'm going to draw it out on the right. Low frequencies are passed all the way up to FB. So you draw a straight line in the passband, meaning no attenuation, right? Whatever input you give is obtained at the output without any degradation. So this is the low frequency asymptote. And this would be the high frequency asymptote. An actual curve would perhaps look something like this. Right? It's like a curve. A big difference with Bode plots is you have two straight lines, and both lines would meet up at FB. Okay, both lines meet up at FB. Again, FB is the border between the pass and the block band. So whether it's the low frequency or the high frequency asymptote, both asymptotes will meet at FB. Does that make sense? Let's take a pause, think on that. Let me know if you have any questions. Any questions? Okay. So that was for low pass filter. How about high pass filter? What would the high frequency portion or the high frequency asymptote for a high pass filter look like? Just the high frequency portion. Flat line, right? A straight flat line, because the high frequencies are passed through for a high pass filter, right? And then the low frequency asymptote, of course, would be slow. The slope for both filters always has a value of 20 dB per decade. 20 dB per decade. And this is something we will look at in detail, well, a little bit more in depth on Wednesday. Okay. The y-axis is plotted in dBs or decibels, and the x-axis is the log of the frequency. So it's not a linear chart anymore. It's a highly compressed chart. And what it does, it allows us to plot a very wide range of values in a very small chart paper. Okay, very wide range of values, small chart or small graph. And so we'll look at what dBs are, and we'll look at what decades on Wednesdays. But this is a short answer question on homework that is due tomorrow. So I wanted to cover this. This 20 dB per decade, the value of 20 comes from the fact that it's a first order filter. First order filter is 20, second order it's 40, and so on and so forth. Third order is 60, fourth order is 80. So the slope becomes sharper and steeper as the order of the filter increases. There are trade-offs. There are a lot of trade-offs. So depending on what your application is, you might want a very sharp curve versus a degraded performance in some other area. And again, as I stated, filter design is a specialized field within electrical engineering itself. Okay. We only study first order and second order. Second order filters also just the resonant bandpass filters, nothing else. Okay, any questions? Good. Okay, let's look at the example problem then. Oh, hold on. Stop share for a second. Okay, so this is a problem where we want to calculate the output of a filter circuit. The approach is similar to the example problem that we saw earlier in this chapter. That first example, we had a transfer function of a circuit given to us. The circuit itself was not given. We were given the transfer function in graphical form, and so we obtained the output for a specified input. Here, the question is again, what is V out of t given a specific input V in of t? So V in of t is given to us, a circuit diagram is given to us, we are asked to calculate the output voltage. Output voltage is a function of time. Okay. Now, we studied 4 different filters so far, so we already know what kind of filter this is. But if this was an unknown filter, then the first thing we would do is we would determine what kind of filter it is so that we know which equation to use. That's the absolute first step. So we do the quick analysis using component behavior at low and at extremely high frequencies. We draw 2 circuit diagrams, one for f is equal to 0, the other one when f tends towards infinity. And when f tends towards 0, capacitor is open circuit. F tends towards infinity, capacitor behaves like a short circuit. So at high frequencies, output is equal to 0, meaning output is blocked. At low frequencies, output is equal to the input voltage. So it behaves like a low pass filter. Right? It behaves like a low pass filter. Now, if it's a low pass filter, we have the standard expression. Standard expression is h of f is 1 over 1 plus jf over fb. That's the standard expression. If it was a high pass filter, it would have an additional term in the numerator, jf over fb. Right? In example 1, early on in this chapter, the transfer function was determined using the graphs that were given to us. Here we already know the equations. We just need to decide which one to use. The decision is based on what kind of filter it is. So low pass filter, we use this equation. Next step is to calculate FB. FB for a RC filter is standard 1 over 2 pi RC. And that turns out to be 100 hertz. Value for R and C are given to us. Okay, so we calculate break frequency, it turns out to be 100 hertz. Then we look at the input waveform. Similar to that earlier example, 3 components. The 3 components have the exact same values, the exact same magnitude, and the exact same phase. 5 with an angle of 0. So the phasors for all 3 are exactly the same. It's the same vector. 5 with an angle of 0. Does everyone see that? Right. The only difference is that the frequency is not the same. And that is the big difference. If frequencies are not the same, you cannot combine them. So we have to treat them individually. Okay, we have to treat them individually. There, in a DC supply, you could have, 2 or more power supplies connected in series. You could add them up. In the AC, you cannot do so. The frequencies are different. You have to treat them independently. So you analyze them separately, breaking it up into 3 parts: V in 1, V in 2, V in 3. And we extract information about frequency in hertz because our transfer function is a function of frequency in hertz. So we want to obtain F1, F2, and F3. We take omega, equate it to 2 pi F. So 200 pi equals 2 pi F. 200 pi equals 2 pi F. 2000 pi equals 2 pi F. All 3 equated gives us 10 hertz, 100 hertz, and 1000 hertz. Now we know which frequencies we have to analyze. Let's take a pause. Let me know if you have any questions thus far. So far, so good. So which step are we talking about? Oh, this one? That is the input signal that is given to us. Yeah. Yeah, that's the input signal V in of t that is given. Let's see, any other questions? Yeah. Absolutely. So the question being asked is, wouldn't a frequency of 1000 get blocked? And that is what we will determine. So h of f is f1, f2, f3. We plug in the values of f. Again, f is the variable. So f has 10, has 100, and has 1000. And we obtain 0.1, 1, and 10. Okay. So for f1, h of 10 becomes 0.1, j 0.1. For h of 100 is 1j, and h of 1000 is j10. Again, fb is 100 hertz. f1, f2, f3 are the variables. So 10 over 100, 100 over 100, and 100 over, 1000 over 100. And you obtain the transfer function. If you have a programmable calculator, you can take this entire equation and program it in there, and it will simply give you the final answer like this. Okay. If you don't have one or you don't know how to do it, then you would do a manual calculation like how I have done. And since I'm performing a division, I'm taking 1 and dividing it by 1 plus j.1. I can represent it in polar form as 1 with an angle of 0. And in the denominator, I would convert the 1 plus j.1 into its magnitude and phase, polar coordinates. Okay. Again, if you have a programmable calculator, you can program this equation directly in there, which I think most of you do. So you program this equation in there, you should obtain this value. If you're like me and solving this manually, then I would convert the denominator into these polar coordinates and then perform the division to obtain the answer for h of 10. Similarly, you'd find the answer for h of 100 and h of 1000. Once you have those, you simply take the standard equation. H of f is V out over V in. So V out is H of f times V in. Multiply it 3 times, form the 3 calculations for H of 10, H of 100, and H of 1000, and you'll have your final answer. Let's take a pause while you think over all of these steps. Let me know if you have any questions. Any questions? Does the approach make sense? Transfer function, individual transfer functions at specific frequencies, and then multiply it with the input, because it's displaying how the circuit affects each component at its specific frequency. So if we look, this is our FB, right? Right here. So we'd expect ideal filter to be like this. All frequencies lower than 100 should be passed without any effects. If you apply 5 volts, there should not be any attenuation or any deterioration of the signal. We should obtain 5 volts at the output. But that's not the case. Real life filter, even at 10 hertz, you do not obtain full 5 volts. It's 4.975. This is the reason why I took so many significant digits or decimal places. So here, the reason I took so many decimal places is so I'll be able to have an even more accurate answer, right? Instead of 5 volts, it's 4.975. Obviously, we can round it up to 5, but you see my point. There's always some attenuation, some effect of the circuit on the input signal. At the break frequency, the output voltage will always drop to 70% of the input. So you get 70% of the input, or 70.7. It'll always be 0.707 with an angle of minus 45, always. Because if your input has the exact same frequency as your break frequency, you will always obtain 1 plus j in the denominator. If your break frequency is 1000 and your input is 1000, you'll get 1 plus j. 11,500 and your input is 11,500, you'll again get 1 plus j. So V out at the break frequency, doesn't matter what kind of filter it is, will always be 0.707 times your input voltage. Output voltage will drop to 70% of the input. Power is given by V square over R. At break frequency, voltage is 70% of the input, but the power is only 50% of the input. If input power is 100 watts, then your output power at that break frequency will only be 50 watts. Okay, hence the break frequency is also known as the half power frequency. Okay, half power frequency. So break frequency, cutoff frequency, half power frequency, they all mean the exact same thing when it comes to filter circuits. Okay, FB, FC, half power frequencies. That is the point, that is the border between the pass band and the block band. That's the transition point between the pass and the block. And then if you notice at 1000 hertz, 1000 is 10 times larger than your break frequency, right? Your break frequency is 100 hertz. Input frequency is 1000. You would expect 1000 hertz frequency signal coming in should drop all the way to 0 at the output, right? Output should be short, should not have anything. Yet we still obtain some output. It's about less than 10% of the input signal, but you still obtain something. It's half a volt. So in real life, we design our filters keeping all of these considerations in mind. We would know that we would obtain at least half a volt if the signal is 1000 hertz, but we design it such that the circuit ignores that value. Okay, or you could have a higher order filter in there. Again, depends on the application. Okay, depends on the application. So even though the frequency is 1000 hertz, we still obtain some output. It's not completely blocking it out. All right, questions? Any questions at all? Yes. No, no, this is just the standard power equation from chapter 1. Power is I square times R or V square over R. Which one? Oh, in this equation, you mean? No, this was just for explanation purposes. I just wanted to show because there is a small derivation in there. So obviously I can, time constraints and all, but if students are interested, definitely I'd be happy to talk outside of class. Yeah. Okay, so we'll end class here today and I will see you all on Wednesday when we'll go more in depth.